All right, folks, let's get started. Oh. Okay, so I'm Vivian Zapp. I'm the Deputy Director of the Quantum Science Center, and I finally made it here. I played Oregon Trail on my flight on the way over, but we made it. So I am happy to introduce our morning speakers. So we have two speakers from IBM, our partner in the QSC, and they're going to give kind of coordinated talks. And so our first talk from Nick Bronn, who's a quantum researcher at IBM, will be on quantum simulations, simulating quantum dynamics using programmable quantum computers. And then our second talk is going to be on error mitigation. So these two closely related subjects will be linked, and I think they have some hands-on exercises for you as well this morning. You can also continue this evening if you don't finish them. So, all right, so welcome again, and without further ado.
Nope, I got this. Can everyone hear me okay? All right, great. Thank you so much. Thank you, Travis, for the honor of coming here to speak to you. Thank you, all of you, for your attention this morning. I'd like to say a couple things first. One is that me and my colleague Vivek will welcome questions. We'd like to make this as interactive as possible so that you get the most out of it as possible. On top of that, we have a tutorial that we wrote in Python and using Qiskit, where I executed some experiments yesterday. It's not really an exercise for you, but I think I can distribute it freely, and you can try and exercise these on your own in your own time if you like. I think the second thing I'd like to do is just say that I am an experimental condensed matter physicist by training. I have been doing kind of coding and hands-on using our system as clients would, not in the lab, for the past 4 years. So quantum simulation was kind of the area that most naturally fit into me. So I kind of have that perspective. But I also want to say, because of that, I used to build the hardware, so I know a lot about it, and I'd be happy to kind of entertain questions, because a lot about how the hardware works is the reason why we have to deal with the certain kinds of errors today. And while I'll be talking about errors in kind of a general sense, my colleague Vivek will go into the specifics of the error models in the second part. Okay, so please raise your hand or anything. I see everyone. If anyone could let me know if people are on Zoom with questions, that would be great. So the motivation is why I simulate quantum systems. I'm going to open up with that. I'd like to thank John for his excellent talk yesterday that kind of warmed everything up. Thank you, John. And I think he introduced a lot of things that means I don't have to cover them or spend so much time on them today. So then I'm going to talk about our open source software development kit called Qiskit. And in particular, we have a new model called Qiskit Patterns for how do you think about not just simulation problems, but solving problems on a quantum computer in general. And then we're going to specifically go into the quantum simulation problems, such as how do you map the problem to a quantum computer? And this consists of moving the Hamiltonian that you want to study into something that you can run on a quantum computer, decomposing it into something you can turn into gates, and how you go about measurements. And then we'll talk about how you optimize quantum circuits. I think this is probably where I think about things the most, because you know where the error is, you know how the superconducting hardware works, and of course everything is changing all the time, so you can never rest. Then I'd like to introduce questions and contact info, and then we have a code tutorial that I mentioned earlier. So we will go through it like that. Okay, so we all always go back to this original slide of like Richard Feynman, 1981-ish, I think. He was the one that had these problems that take place in a large Hilbert space in which the problems are intractable by solving them using unitary evolution and diagonalization and the techniques that we know. Basically, the same thing that was talked about yesterday is you can write down the equations, but there's so many of them that you can't actually practically solve anything. So he speculated that if you had a computer that actually obeyed the laws of quantum mechanics, then you could map the problems to that quantum computer, and then you could solve the problems. But of course, that's not such an easy thing to do, but it is interesting, and so that's why we are making our careers out of it, I suppose. Okay, so why do you want to study quantum systems? So this is kind of a background of, maybe some of the problems that I think about, mainly coming from material science and chemistry. For example, like high temperature superconductors. High temperature superconductors were discovered by the IBM Zurich lab in 1987, so like 35 years ago. However, there is no successful microscopic theory of them to date. We have a theory since 1967 of how low temperature superconductors work, but they do not apply to these kinds of things. And one of those things about these high temperature superconductors is a lot of the ones, especially the ones that were initially discovered, are something called a class of materials called cuprates, which tend to be brittle and hard to manufacture things. So if we had the ability to more easily manufacture things, like if we could treat them as metals, we could say build high energy transmission lines, for example, where, you know, right now, according to this Nature climate change paper, 5% of all of energy and electrical transmission is wasted, or in electrical production is wasted due to the transmission costs. So you could easily get rid of some amount of power, and that would be good for the environment and good for the economy, for example. And it would be very good for Vivian if there was a very large network of high-speed trains, for example, a maglev, because we could use the same thing because the superconductors repel the magnets. We can build maglev trains out of it. So the technology for the economy and travel and convenience could be improved. Another example is catalysts, for example. This particular catalyst specifically does something equivalent to what is called the Haber-Bosch process, which was a process discovered over 100 years ago, a chemical process that takes the environmental nitrogen that consists of 80% of what we're breathing right now and fixes it, meaning it takes the triple bond and turns it into something singular bonded, meaning converting to ammonia, basically. But that ammonia is basically plant food, and it can be consumed by plants in that manner. And it's responsible for feeding about 2/3 of the world's population. So that's a lot of you. 67 of you are alive today because of this process that was invented. However, that process is very expensive. It consumes 2% of the world's energy because it operates at 400 degrees Celsius and 200 atmospheres. So just to put in like a couple of my favorite kinds of quantum simulation problems that you can immediately kind of assign economic and business value to, on top of, you know, climate change and stuff like that. The one thing that we know about this catalyst is that our friends, these cyanobacteria, actually they fix this. They fix the nitrogen from the air at ambient temperature and pressure. So we know that you can actually turn the nitrogen you breathe into nitrogen that plants can use at ambient temperature, but we don't know how to do it because we don't understand how the catalyst works. And these are mainly because these things have complex transition metal catalysts where the chemistry problems become too hard to solve. And then other things that are maybe more relevant to people in this facility, for example, the Quantum Science Center is tasked with developing topological materials to build devices that maybe will perhaps build the next quantum computers. Maybe perhaps there'll be a lower power way of doing computation, because we all know AI is eating a lot of energy as well these days. And then one of the other things that my colleague Bibek will talk on a little bit more is now we have near-term algorithms that I'm going to talk about today, but Bibek will go into more detail, where we can be competitive with the best tensor network models. So we are at the point where the quantum simulations can be competitive with the best we can do classically, to within all of them kind of disagree to the same amount. Okay. So I know not everyone's a physicist in here, and I always like to ground my talks in something that everyone understands. So we're going to start with the Schrödinger equation. I think that's fair enough. So the Hamiltonian describes the energetics of a quantum system, and it evolves in time according to this equation. This equation isn't exactly important. Rather, its formal solution, where you have the dependence of time of the wave function, is equal to e to the minus IHT times the initial state of that wave function. And we also call that e to the minus IHT. That's a formal solution because that is an operator right there. That is a unitary evolution of the quantum state from time t equals 0 to some arbitrary time. And this is kind of the basis of what we're going to talk about today. Now, you can extend this to time-dependent Hamiltonians, for example. You can always make this more complicated. So, for example, you have a formal solution of a time-dependent Hamiltonian given by this time ordering operator operating on the initial state. But basically, we don't need to go into that level of detail here. We can always know that we can always we can make things more complicated and we can bring it back to kind of the simple understanding. So I'm going to stick with simplicity today, and we're just going to stick to time-independent Hamiltonians. Basically, we'll talk about quench models we turn on at time t equals 0. But I'll touch on a lot of other things as well. The other thing I want to say is that I'm going to be focused on these quantum simulation algorithms on near-term hardware, not fault-tolerant hardware. I'll make the difference between these two, but that really affects about how you approach these problems, because kind of the textbook examples that we know for quantum simulation are going to be untenable on anything that exists today or in the near term. How are we doing? Questions, anyone so far? Schrodinger's equation? Okay, good. Yeah.
So in simulation, do you assume unitary time evolution, or are there any versions of this that you could assume non-unitary time evolution, where you have some sort of objective collapse of the wave function?
Yes. Okay, so the question is that I'm assuming unitary time evolution, and the answer is no. There are always more crazy ways to do, such as imaginary time evolution, for example, or projective measurements, and I'll discuss those. Well, I'll touch on those at least a little bit. So there's a whole bag of tricks that come to you in quantum simulation. I'm going to try and show you the most straightforward example, and that will be the same thing as the code today, but I'm going to touch on some of the things that you mentioned. So thank you for that question. Okay, so Qiskit patterns is kind of a method we developed at IBM to talk about how we approach quantum problems in general. It's mainly a framework for thinking about kinds of things. So you want to map whatever problem you have to the system. This is relatively straightforward for quantum systems because everything obeys quantum mechanics. But if you have an optimization problem or a finance problem, then there's ways to do that as well. You want to optimize for target hardware because you have a limited connectivity. You have limited gates that you can do, single and 2-qubit gates. You're typically limited to which entangling gate you have. Then you want to execute this on target hardware. That is going to be how do you kind of manage these workflows if you're like, hands deep into running jobs like you would, on Frontier at Oak Ridge, for example. How do you manage those kinds of jobs? Similar, how do you manage jobs on an IBM backend? And then post-processing the results, typically this applies to error mitigation, trying to get rid of errors. This is going to be something that Vivek will discuss. And in fact, I'm mainly covering these first two topics, and I'm going to get a little bit into execution insofar as I execute some code to get you the results in the tutorial. And then Vivek is going to talk mainly about the error suppression and mitigation that goes on in these later types of steps. I should also say there's a little bit of a blur between these things, so I'm happy to talk about some of it if you like now, or I can come back and answer questions later too. Okay, so we're going to talk about mapping the problem to the quantum hardware, because this is mainly the idea of what are you understanding with quantum simulation. Okay, so I like this little picture from this review on quantum simulation here. Basically, what are you doing with quantum simulation? You have some sort of quantum object that exists in the cloud. You want to study it. It has some wave function phi, and you know that it starts at some initial state. It undergoes unitary evolution on its own. We're going to talk about closed quantum systems right now. We can always extend it to open later. Under this unitary evolution, it's going to evolve to some some wave function phi of t under this unitary right here. The basic idea of quantum simulation is that you can map that problem to some sort of computer. This can be a quantum computer, a digital quantum computer, or an analog quantum simulator. And I would even argue there's a blend of those two, to some kind of state that you know and you can control called psi of 0. And you can map that unitary onto some different unitary, e to the minus ih sim t, and you can evolve that. So if you can prepare and you can evolve that on a computer and you can measure it and you can map the problem back, the hope is that you learn something from the quantum system under study by doing this kind of quantum simulation. Yeah, so that's the basic picture. And just as an overall example that we're gonna drill into a little bit more is we can do say Fermi and onic encodings. So we can have say the orbitals of a molecule or something like that. We can take those electrons. The electrons are not qubits, but they're close enough. We can map those states to qubits, which we'll go into by something called a Jordan-Wigner transformation. And then we can encode the problem onto our quantum computer and study it in an appropriate way. So this is kind of like a high-level idea for what we are actually doing with the quantum computer. How do we approach these problems? Details forthcoming. Okay, so the kind of the overall thing we're doing when we map the problem is we have a bunch of qubits that we initialize in the 0 state. This is kind of what we call the DiVincenzo criteria for quantum computers, is you need to be able to initialize your quantum computer into some known state, and then you can prepare it in some way. And this can be, I'm not going to talk about this too much, but this can be very complex on its own. I'm mainly going to talk about, once we have that state, how do we evolve it in time, and then how do we actually measure it and get results out. So there's kind of 3 parts. State preparation, time evolution, and you're measuring the observables. And there's different ways you can approach that. So we'll go through all of those, and then we'll do an example of the easiest one. Okay, the other thing I want to talk about is another thing John talked about yesterday, so hopefully this is already in your head, is we talk about statics versus dynamics. In statics, we are thinking that we have a system that is weakly coupled to a bath given by some sort of inverse temperature. So in some sense, this is not really a pure state, but it's a thermodynamic state with some sort of partition function where it's weighted by these Boltzmann factors. And what you can understand is you have this density matrix, which is going to be a probabilistic sum of pure states weighted by these Boltzmann factors. And if you're in the regime where you have a lot of relaxation, or your temperature is less than the lowest energy level transition, then typically you can describe things by the ground function, by the ground state function, wave function. So your ground state energy is going to be the minimum of this expectation value of the Hamiltonian. And this is how you solve a lot of problems, both classically and quantumly. And the way you do that is often quantum mechanically and classical mechanically. You can use variational techniques or other heuristics. There's a lot of tricks that you can apply to this kind of problem, and that's usually because there's a lot of structure to the ground state wave function that can be exploited. And so these aren't necessarily very difficult for classical computers to do. However, when you approach dynamics, you want to evolve and measure observables called O, and you start with the system, say, in some ground state or some state you prepared. And you can, say, do things like a quench. You can turn on a Hamiltonian from H naught to H, and you can observe an operator that is time evolved by calculating the e to the minus IHT, and then taking the bracket of that. Other things you can do are a little more complicated. Say, for example, if you look at that, you could, I probably introduced this in the Schrodinger picture, but if you convert to the Heisenberg picture and you have the time evolution of the operators, then you can write the operators a function of time as e to the IHT O times e to the minus IHT. And then you can calculate correlation functions between different observables at different times. So this is very useful as well, because this often corresponds to things that you measure in the lab. In fact, one of the important things is if you take the Fourier transform of this, you get the spectral function, the structure factor, which is something you can measure in like neutron scattering experiments, for example. So this most closely resembles the things that you measure in the lab. And one of the things that you would want quantum computers for is to validate the models that you have of the theory, for example, and you can test those out by computing the answer given different models and see if they correspond to what you get in the lab. Sorry, question over there. Yeah. H naught would be like kind of the system Hamiltonian that it's just kind of sitting under, and then you just turn on some Hamiltonian at some given time. So in some way, I believe in the paper that Bibek will present, we call it the kicked Ising model, in that we just turn on some Hamiltonian time t, but the qubits are just sitting there in the ground state of their transmon Hamiltonians, in the fridge in the lab before you do that. So kind of everything has a Hamiltonian, and I refer to the H naught as kind of the ambient Hamiltonian as the system behaves. So you could just pretend like it's 0, for example. It's not doing anything. Yeah. Sure. Okay, so the question is, am I preparing some sort of topological state? It could be a topological state. You can prepare whatever state you want. I mean, a lot of them are harder than others. We're going to start in the ground state because that's the easiest one. But then yes, you evolve by unitaries after that. And then I believe there was one more question. Yeah. Okay, so the question is about, can you add a bath at a certain temperature and such, like, can you prepare states like that? Yes, that's exactly kind of a big subfield of this called Gibbs state preparation. Exactly. So this is something you can do. You can prepare these as open systems. I'm just talking about as a closed system because it's usually easier to think about Schrodinger's equation instead of the Lindblad master equation. So kind of like everything I want to present here is like, there's a lot of variations, and I really appreciate your questions because you really are seeing the opportunities of this. And the answer is generally yes. So you're going to find a way to be able to simulate any quantum system on this, but you just kind of have to expand your idea of what I'm talking about here. So yeah.
Right, so is there an advantage to going to the Heisenberg picture here from the Schrodinger picture, or could you solve any?
So the question is the Heisenberg picture versus the Schrodinger picture. I mean, I think it's always a preference to what do you use? I think I usually think in the Schrodinger picture until I do something like that. Yeah, I treat this as kind of like a problem, like which one's more convenient to use at the time because they're equivalent. Yeah, I mean, I use the interaction picture a lot too. So any other questions while we're here? Oh, yes.
Of that side, like what do you mean the Gibbs state and then described by the Bronn state?
So sorry, this is only in the low temperature limit. Sorry, I think that's a very good eye. I think I forgot to put the low temperature limit on the slide. But it was supposed to be when KBT is much less than the transition, the ground to first excited state transition, then you have this limit. And yeah, I forgot that part. So thank you. Thank you for correcting me. Yeah, thank you. All right, this sharp crowd, this is great. Question. Yeah. I mean, the idea is that you can prepare any known state. Coming from a hardware background, I usually think of the DiVincenzo criteria as kind of the what do you require for a successful quantum computer, and usually the fact that you can initialize it. Usually people like the ground state, all zeros is fine, but it doesn't have to be. And I mean, often you want to build a complicated state. So if you can build a complicated state that isn't all zeros, then that's fine. But I think the idea is that you need to know what you're starting with. Yes. Oh yeah, there's a very general kind of synthesis of these circuits that we're gonna talk about. So yeah, basically. So the question was, is it a parameterized circuit? Yeah, we usually will talk about time being the parameter, basically, which is actually an angle of rotation in the Hilbert space. Yes, in the back. For degenerate ground states. That is a straight preparation question I probably don't know the answer to. If you can prepare it, you can evolve it. I mean, you can certainly prepare degenerate ground states. I guess what is the question? Oh, so degenerate time. Okay, yeah, exactly. You can do all this. Yeah. You can map all the problems that you saw Chetan talk about to qubits. Those Majorana fermions, there's a mapping. It's a variation of the Jordan-Wigner mapping that you can use as well and do the same kind of thing. In fact, I've done the same kind of thing. All right, great. All right, I need to speed up a little bit. Okay, no, this is great. Please continue with the questions because I think this is how everyone's going to learn best. So I just want to highlight the quenches. We're going to talk about a very simple system. We're going to turn on a Hamiltonian at time t equals 0. This is also very similar to the system Vivek will be talking about, the kicked icing model. Here's another thing I reviewed when we had some other interns. We wrote a little review paper about how you can think about quantum simulations. And now, like, I mean, even after a year or so, I would add a lot to this, but there's just kind of like a workflow that we think about, or you can check out this paper. But it's the same kind of idea as a Qiskit pattern. Is you're going to identify the system Hamiltonian. You need to map that to a quantum computer using Hamiltonian coding that we'll talk about. You have to worry about preparing the state, evolving the state, and measuring it, and then you have a lot of error mitigation opportunities and error suppression opportunities before we get to the era of fault tolerant error correction that you can take that will take place in the future. And then, you know, there's kind of like I guess the only reason I kept the slide in is because I want to show that there's like a lot of different ways you can do this. So you go through this flow chart, you can pick a lot of these things. Sometimes you can pick multiple things, and you will kind of like live or die by the choices you make when you try to approach quantum simulation problems on near-term quantum hardware. Oh, I thought there was a question. Okay. All right. So then how do we think about these kind of first things? We start from like, you know, your basic undergrad quantum mechanics class, and we think about first quantization. What are we doing? We have a wave function of a single particle, but what happens when you put many particles together? Those wave functions are going to need to start obeying some symmetries, and we classify kind of the states of matter depending on whether those wave functions are symmetric. Whether when you exchange two particles, you get a plus sign at the wave function. We call those things bosons. We also have antisymmetric wave functions, such as when we change the position of two particles, we get a minus sign in front of the wave function. That's antisymmetric, and we refer to those as fermions, which typically make up matter. Now, of course, there's anyons and topological materials as well, but we're not going to talk about those today. Basically, I just want to give you this idea is that these things are important to consider because when you do the simulation, you need to respect the symmetry of the problem at hand. And there's different ways of doing that, and that has a lot to do with how we do the encoding of the Hamiltonian. So if you have these wave functions, you usually enforce these symmetries by permanents or Slater determinants based on a slew of single particle wave functions that you combine to make your mini particle wave function. And this is hard. This seems I don't know. It's hard to me, but it's kind of what my quantum chemist friends do. I prefer to think in terms of second quantization, where you kind of have an idea of a harmonic oscillator type structure, and you have creation and annihilation operators. Then you can encode your symmetries into those creation and annihilation operators, and you can have something like A's and A daggers, which is used to represent bosons, and they have a commutation relation where commutation AI AJ dagger minus AJ dagger AI is delta IJ, and then different particles commute. We also have anti-symmetric ones that obey this commutator, and I usually use C's to represent fermions because that's what they obey. And they have this other thing, but you have a plus sign there, which means when you're on different fermions, they're going to anti-commute, and that's very important for mapping to a quantum computer. But basically, if you pay attention to these relations, these will enforce the symmetry constraints of your problem. So you don't have to worry about Slater determinants or permanents anymore. You just kind of know that you have an encoding that obeys these equations, and you're good. Okay, so we're going to focus only on second quantization. I would also say, you know, first quantization has a number of people working in it today. It kind of depends on the number of modes you have in your problem and the number of excitations. So if you have a lot of modes and a few excitations, I think the first quantization approach might be easier, and vice versa for second quantization, because each one of those modes is going to take up at least a qubit, basically. So the more modes you have, the more intensive your computation is. Okay, so specifically talking about modes, how do we map these to qubits? So I'm going to talk about capital N excitations. So how many quanta of energy do we have in our system, and how many available modes do we have for those quanta of energy to occupy, with a total of lowercase n, or I guess that should be uppercase n. So for bosonic systems, we can apply the creation operators to the vacuum state of all zeros in some way where we can apply any number of n. Because these are bosons, they can be any arbitrary occupation of these things. The order in which we create them doesn't matter because the excitations commute, but you do have this kind of annoying factor out front. We're not going to really talk about bosonic simulation today, but I'm happy to. I do a little bit of work on it. The kind of point is to show you can create any state you have out of these creation and annihilation operators. The fermionic one is a little more interesting in that you can only have 0 or 1 occupation due to the anti-symmetry of the wave function. That means that, or that's exactly what gives you the Pauli exclusion principle. So you can only have 0 or 1 particles of your state, but you kind of have the same idea of creating this from the vacuum state. And in this case, the order in which you create these excitations is important. So you have to be very specific. Okay, now we move to qubits. What physics do qubits obey? Well, they're not really bosons or fermions, but they kind of have some similarities with bosons, but not exactly. They have a commutation relation that looks somewhat like that, where you can do the commutator of a lowering operator on a qubit and a raising operator on a qubit, and you'll get delta IZ times the Z Pauli operator. So I'm writing, I've kind of switched between these raising and lowering operators and the Pauli XYZ kind of alphabetic notation back and forth, and I'll usually kind of go towards the alphabetic notation a little bit more. But basically, you can represent the lowering operator of a qubit as sigma minus, which is x plus IY. And one thing to note here, because this always causes confusion, this is the opposite of spin raising and lowering operators. So if you have a spin up and you want to go down, that is the opposite of an excitation in qubit land. So spins go up and qubits go down and vice versa. This is, yeah. Unfortunately, the physics is exactly the same between qubits and spins, except we have this kind of difference because the ground state energy is aligned along the positive Z axis of a magnetic field. So spin up is always the lower energy and spin down is the higher energy. So spin up represents 0 and spin down represents 1. That's why it's opposite. So just be careful if you're ever doing calculations or someone gives you homework or something like that. So because basically if you have different qubits and different qubits, they commute, then how do you represent fermions with qubits? Because they don't obey the same anti-commutation relations. Well, the answer was solved a long time ago by Jordan and Wigner, and they said, well, what you can do is you can just use the same raising operator, but instead of when you go down the line of encoding the modes, you need to increase the number of Z's you have here, and by increasing these Pauli Z's in front of you, you can enforce the same symmetries. And so this is something called the Jordan-Wigner encoding. Basically, you have your first electron is created the same way as a qubit is created or excited. And then each one you create after that, you need to put the string of Z's here. And those string of Z's will enforce your commutation relation. I'll talk about a little bit more, I think, on the next slide. But this is the one we'll use today and kind of the one that everyone knows because it's been around for almost 100 years. Yes, question in the back. It should be capital N. Yeah, sorry. I thought I said that. Yeah, I had a typo. That should be capital N. So for the Zoom crowd, I was just pointing out that the first equation, the sum on Ni, should be capital N on the right side. Okay, so the question is, how do you take care of these schemes because these things are not unitary? That's a great question. So what you do when you combine these, you'll build a Hamiltonian, which is Hermitian. And then when you have e to the minus IHT, that is unitary. So when you build a Hermitian operator, you can then do unitary evolution from that. So these operators are not exactly what you're mapping to the qubits. I'm going to show you how you actually build the circuits that you operate on the qubits using these kinds of terms. You can use these to prepare the state too. Yeah. Right. Okay, so I guess let me say you can do non-unitary like state preparation. So for example, what we'll do today, my state preparation was ground state, and I'll just excite one qubit on the end, and I'll just hit it with an X gate. The main thing about doing these transformations here is we're converting the Hamiltonian from a fermionic or bosonic Hamiltonian to a polyhamiltonian. So consisting of these kinds of XYZ strings. That's something that then we can map to a quantum computer. You don't, I'm usually thinking about these in terms of evolution, but you can think about these as just applying an excitation, because you are kind of free to do that as well. Hopefully it's clear when I show examples. So this is still like very high level. We're gonna get into very like, how do you actually do this kind of techniques later. But I would say like, I mean, even your X is like a unitary, but you're putting energy into the system. Okay, so we're going to continue talking about Hamiltonians. We kind of like have a zoo of quantized Hamiltonians, and as a condensed matter PhD, we love these toy models because the idea is that you have 10 to the 23 electrons flying around in a material. You can write down the Schrodinger equation for each and every one of them, but you can't solve those problems. So in condensed matter physics, and probably particle physics as well, you can write down these effective models where you can understand the physics of some device or some interaction without having to understand all the physics, but you can extract the essential physics. So this Hubbard model, for example, what we're doing is we're going to have some sort of hopping energy where states move from fermionic mode I to J, but they maintain the same spin sigma. So the Ci dagger Cj means I destroy a particle at site J, I create it at site I. It corresponds to moving, but I'm going to keep the same spin sigma. The second term is the electron-electron interaction. That is something that happens in like say strongly correlated systems where the electrons really feel the strength of the other electrons. So on the same site I, the electron that spin up feels the Coulomb potential from the electron that spin down. And this is kind of a simple model of a lot of materials, including some strongly correlated materials. There's chemistry examples, for example, the kind of molecular Hamiltonian a lot of people use it's called a singles and doubles type Hamiltonian, and it consists of kind of the same thing where you have a hopping term given by these T coefficients and your interaction coefficients given by these nus, which is a two-body interaction as well. Yeah, one thing I want to say here is these coefficients here, these are determined by you're choosing a basis that you're mapping your problem onto as well. So these are basically given by overlap integrals. These overlap integrals are actually classically easy to figure out. So we kind of treat it as trivial as you go from some, say, molecular wave function, such as the 3D Gaussian wave function or whatever, to these kinds of T's and nus, because you're just going to do like numerical computation of these wave functions. And there's a lot of libraries out there that exist to kind of do this for you. So another one that I like a lot is the Jaynes-Cumming model, which is a spin boson interaction model where we have the say a cavity, an atom inside of a cavity. So we have some sort of energy associated with the cavity, and we have the occupancy, the bosonic occupancy operator there. And then we have the state of the spin, whether it's up or down. That represents the atom or qubit. And then you have an interaction between the bosonic mode and the spin mode. And the reason I like this is because this is kind of the first Hamiltonian that you write down to understand how qubits work, and this is how you start designing qubits, for example. So the superconducting qubits I'll talk about, they obey the same kind of wave function as this, and that's kind of, even though it's a material that consists of 10 to the 20 electrons or so, it can be understood as a very simple model like this, and you can extract a lot of information out of it, even with this kind of a simple model. We also have Heisenberg models. These talk about spins in certain spins in materials. So you can have higher order spins other than 1/2, for example, that you can map, and you have a spin-spin exchange interaction given by these J's, for example. You can also do superconducting type Hamiltonians, where we have not just a hopping term, but we have this pairing term. So Chetan talked about this a bit yesterday. You have this gap. And then we kind of have like impurity models where you have defects inside of a system that can influence the behavior, where your defect creation and annihilation operators are given by these Ds with a certain characteristic energy. Then you have your normal electrons in the system, and you have some potential between those defects and the normal electrons on top of a electron-electron interaction for different spins. So these are kind of like very, very, relatively simple models because you can write them down in one equation that try to elicit a lot of deep physics of these systems. And so, validation of these models and comparing them to experimental data is necessary to see if they're accurate. And that's something that quantum computers are kind of, hopefully will do in the near term. And the other thing about these is that I'd like to point out is that a lot of these Hamiltonians only have two terms in them that are called quadratic Hamiltonians. Those can be actually solved exactly, such as models like the Fermi liquid model, for example, how you understand your basic understanding of electrons and semiconductors and metals and stuff like that. You can analyze that more. You can analyze that easily analytically, or you can solve it relatively exactly by introducing quasi-particles. The tough thing is when you have these four body terms, for example, in the chemistry Hamiltonian here, or the impurity models. These strongly correlated Hamiltonians are very difficult for quantum computers to solve at scale. These are the kinds of problems that are going to be the ones that we really need quantum computers to solve, whereas the other ones with the two-body terms, for example, could be thought of as maybe test cases for quantum computers where we can solve something analytically and then we can benchmark the quantum computer against how well the system replicates the answer. And those are kind of the two sides I think about these Hamiltonians. You have the easy ones and the hard ones. You can use the easy ones for validation, the hard ones for actually scientific exploration. And then the other thing is, maybe you notice even some of these Hamiltonians don't obey particle conservation, which is also interesting because in this case where you don't have conserved number of particles, you have to introduce, generally more modes and more degrees of freedom to be able to map your system. So these also get kind of harder. And that especially is the case with bosonic modes because there is no cap on the occupation. You have to set that yourself when you figure out the problem. Question?
Are all of the terms in the impurity model?
Oh man. Okay. Epsilon D is the defect on-site energy. Epsilon K is the I guess wave function energy. VK is the hopping between the defect and the band CK, and U is the on-site energy between spin up and spin downs on the defect. Yes, another question.
Is there a sigma?
Oh, this is for both spins. Oh, sorry, that should be independent of that. No, sorry, the sums are independent sums. So the question is about the impurity model. The first sum is just the defect term over sigma in front of the second.
Yeah, that's one question.
Oh, whoops, that's a typo. Sorry, that sigma in front of the second sum should not be there. Sorry. Another question. Sorry.
The gains coming from Hamiltonian here that actually doesn't concern the number of particles.
Right.
Do you use like rotating wave approximation to actually get rid of the data?
The question the question is about the Jaynes-Cumming Hamiltonian, which does not conserve occupation. The question is about the rotating wave approximation. Absolutely, I would absolutely use a rotating wave approximation because this is a much harder problem if you don't. Because you have to figure out what your occupation cutoff would be. So you kind of have to run a bunch of simulations to see where you saturate that, where you can actually set the cutoff, and that's just a lot more work. Oh yeah. I think I mean, so like I would add like excitations and stuff like that, and there's always problems that don't conserve number of particles, but I would say usually the focus is on making sure your circuits are conserve the particles. So like for our chemistry ansatz, I'm not really going to talk about VQE, but you want to have an ansatz that conserves particles, because if you have something that's kind of unphysical to your problem, you just don't want to do it that way.
So like I know that's four body already really difficult to solve? Have you solved it harder, like six body?
Oh, so the question is if you want to do multi-body problems, like 6 bodies and stuff like that. Yeah, I mean the answer is yes, you can absolutely map those to quantum computers. Of course, it's going to be harder for quantum computers, but it's also going to be harder for classical computers. And I'll kind of get into how you can map these problems. Like there is a kind of straightforward synthesis of these problems onto a quantum computer, but the higher weights of the observable, and by weight, I kind of mean how many non-identities are on the polystrings that represent the operator that you're going to map to the quantum computer, the harder it is going to be in general, because the circuits will just be deeper. But I'll show examples, so hopefully that becomes clearer. Yeah, no problem. Is there another question? None of them. No, I would, just kidding. So I would start with the Kitaev model, which is very close to the BCS Hamiltonian. You need a mu times the mode occupation. So you need a chemical potential term, and then that's a good starting point. But if you want to talk later, I can show you some work I've done on that. Okay, cool. All right. This is awesome. Okay, so all right, so we're going to go through operator encodings, and I'm really just want to give you an overview. Oh, I did want to say one thing on the last slide. We're going to do a tight binding model, which is a very simple version of the Hubbard model, where we don't have spins and we don't have on-site interactions. So it's very simple. We're going to code these Hamiltonians, and there's a lot of different ways you can encode these. So I talked about the Jordan-Wigner encoding, but there's a lot of ways you can enforce the same symmetry of these operators without with different styles. In fact, the Jordan-Wigner encoding, you have these string of Z's, which is interesting because what the Jordan-Wigner does is it encodes the modes locally, but it encodes the parity kind of non-locally and globally. So that string of Z's is very hard to actually represent on a quantum computer. There's another version, or the flip side of that, we call the parity encoding, where you encode the parity locally, but the modes are non-local. And when I say non-local, I mean you just have to have interactions by a bunch of qubits. You get higher weight poly terms. So your circuits get deeper because you have to have a lot more C naughts, and that's always bad. And then there's Bravyi-Kitaev, for example, which does a compromise between these two, and you can have some semi-local and encodings of both the modes and the parity. So that will give you, some log n kind of locality to enforce those anti-commutation relations. For bosonic encodings, you can do something like the Holstein-Primakov encoding, which is kind of a complicated way. Maybe when I was thinking about it, you'd only use for like high spin, if you had high spin systems. Normally you would do like a Fock encoding to basis, but you can do things like cat states, for example, or you can build coherent states in actual photonic modes. We don't do that, so I'm not going to talk about that. But when I think about bosonic encoding, I usually move to the Fock basis, which is just the number, occupation number. It's very easy to think about. And the encodings are kind of straightforward. And then for spins, if you have a spin 1/2 problem, then you're in luck because you don't have to do any mapping. You just throw your system onto a quantum computer because the qubits already spin 1/2. If you have spins higher than 1/2, then you can do fancier things like gray codes, linear logarithmic encodings, or potentially even like qtrits or higher order levels of the actual physical qubits. So this is, I mean, none of these examples that I'm presenting today are meant to be exhaustive. There's active research in these spaces. So if you want to talk about that later, I'd be happy to. I'll be around the next couple days. So feel free to come up to me and ask any questions, but there's, so many options here. These are just kind of the ones off the top of my head I would think about. Okay, so now that you have a Hamiltonian, your Hamiltonian is a poly-Hamiltonian, which means I know how to map it to a qubit. Now, the problem with that Hamiltonian is going to be that the terms of those Hamiltonians don't commute with each other in general, which means you can't just break it down into individual exponential terms, like e to the I minus ihit and e to the minus ihjt. Those individual exponentials are what we actually use to map to the quantum computer. So what you need to do is you need to approximate that Hamiltonian somehow in a way that you can decompose it into terms that you can exactly map onto the quantum computer. Okay, so one of these These are called, the ones I'm going to go through are called trotterization models. So the first one I'll go through is the lead trotter method, which is kind of, we also call first order trotterization. So you might do the obvious thing. You might divide each one of those time steps by n. And as you take the limit of n going to infinity, the time steps become smaller and smaller, and you just take n of them. The limit of that will approximate exactly that e to the minus iht. Now that is, all great in theory and stuff like that, but the more of those that you have, the deeper your circuit is, the more you're going to get noise, the more problems you're going to have. So you want to be careful about how you do this. And these kinds of problems are also another rich part of research in here, in this field. So you choose that time step, and basically what you're going to do is you're going to create these circuits that are these small time evolutions of each of these terms, and then you'll just repeat that n times. So I didn't even put the error guarantees, but all these trotterization methods and a lot of the other methods I'll talk about have error guarantees. So if you want an answer to within some degree of error, there are error bounds that you can make for these. You can do a little bit better with second order trotterization, in which you do a t over 2n, and then you start in a similar way as your first order, where you go from 1 to m, but then you go down in the opposite order. So this looks like a circuit where you have e to the minus IH1 and your small time step, and then you get to a halfway point, and then you go the opposite direction. And basically all these errors are caused by the non-commutation of the terms in the Hamiltonian. So you can consider the non-commutation of the terms, and you can think about what that will do for your problem. And if you really have a specific problem, you can really, really think about it. And I'll show some examples of that. But these are kind of the most straightforward ways of thinking about that. So people might also ask, well, why don't you just do a Taylor expansion or something like that? You could do that as well. There are another field of Hamiltonian decomposition called block encodings, which includes linear combination of unitaries and quantum signal processing. I'm not going to talk about those basically because you need a fault-tolerant quantum computer to implement any of those. They have better error bounds, but they don't really work well. They're very intensive in terms of the circuit depth that you need. I see another question over here. Okay. Okay, yeah, so the question is, why do you do these n times? And I think the kind of like hand wavy answer I like is that like you make it small enough so that these terms don't not commute that badly. Right. So the other thing is actually these errors have a way of compounding each other, and like kind of, in a way, you kind of twirl over them in a way that like Vivek is going to talk about error mitigation strategies. They don't compound in the linear way that you might expect, except if you only had like, 2 terms or something. The compounding is nearly not as bad as that kind of scaling. And I mean, there are error bounds on these things, so you can always figure out what number of steps, how small you need to make your trotter steps in time in order to get the answer you want. Oh, question.
Here on the NIST level, the trotterization is that with the block encoding is expensive.
So the question is, why do I say block encoding is expensive? We'll get to that in the optimization section. I saw another question.
At least in theory, circuit tracker is better. Why people often use like less computational expansion?
The question why people use Suzuki trotter over trotter. Yeah, so this first or second order. So if you ask me, and if I was to say like I'm going to digitally simulate this one is twice as long as that one. So in some sense you could do that, but like, there are tricks you can do, such as taking, building these terms out of directly the interaction that you have between qubits, which is something I've done with, where it's not that bad. But if I was to do it digitally, like this is going to scale worse, twice as worse. But I also know if I could like hone the native interaction, then actually the second order is not that bad, because I have the same amount of same amount of effective 2-qubit Hilbert space rotation.
There's like something generally you could say about like if I take n half here, and then I compare it to the first order thing. In general, is the second order thing gonna give me a nicer?
Oh yeah, yeah. Second order, like it's like to the second power, so the scaling is better. For error, the scaling is worse in terms of circuit depth. That's always the trick. I mean, this is always better in theory. Sometimes you can make this.
Instead of having n here, I have n half, so that circuit depth is the same. Then do I know which one
Oh,
does better?
yeah, that's still based error bounds. In that case, I can't figure it off the top of my head. But that's a great question. I can point you to resources where you can actually do that calculation. Sounds like a good homework problem. Question at the end. It doesn't have to be, but I'm talking about only the Hermitian, like just to make it easier. If you want to make it complicated and you want to do non-unitary evolutions, you can make things non-Hermitian, and there's ways to approximate that with unitary things. So I'm going to mention that a little later.
You can have, what you're saying is you don't necessarily have to have a Hermitian Hamiltonian, but you can have you can have unitary operators.
You can approximate it with unitary operators. Yeah. So there's a field called like imaginary time evolution. Yeah. No, there's another question.
Are we not diverting off the unitary part output? Because it's not so the reverse order is not the same. So isn't this going to diverge off?
Okay, so the question is about the second order trotter diverging more from the unitary that we wanted, because it goes in one way and then the other way. So it actually the opposite is true, because the things that don't commute will not commute the other way going. And in some sense. So when you flip things and turn them around, you have a cancellation effect between the non-commuting terms. That's kind of why the second one is better, like in a hand wavy way. Yeah. I don't want to say anything because the techniques are a little bit different. So this definitely applies to unitary evolution, but there is a trotterization for that kind of thing. I know from like the imaginary time evolution, but I don't know the technique well enough to really say in general. So, great question. Another question. Yeah. Right. Okay, so the question is about layering the even and odd interactions. Yeah. I have a slide on that. So that's a very good point. Okay, another question. Oh yeah, absolutely. So if you look at that Kaylin Ferris paper we wrote, we have there's a general recursive formula for the trotter error to any order. So this is very, very extendable. Just in practicality, never go beyond second order.
Yeah.
Yeah. Another question.
I want to have like the smallest form words about these two equations, which is better with terms for the error, because these are twice as big as this for the number of gates, right?
Right.
So this should be worse when it comes to error because I'm applying more gates.
Okay, so the question is about which one's better for error. So like the answer I usually give is like theoretically, the second order, the higher order, the smaller time step is better for your answer because you can write these equations down and show.
Gates?
But on the hardware, it's the opposite situation. These are much harder because you have to go to higher depth if you want to go to those theoretically better orders. So you're in this competition where you have something where you have a theoretically proven result that you can get to on one side, and then you have what will I actually be able to run on the other side, and you have to meet in the middle. So you can't just say which one has a better error because one's going to have trotter error, one's going to have hardware error. Yeah, that's exactly what quantum researchers think about. Thank you. Another question.
Typically, let's say I want to solve a problem. How deep would I be able to go? Like, what can I set n to?
Okay, the question is, what can I set into? I want to give you a flavor for this, like a little bit later, when we actually talk about the hardware, because we're getting there. Any other questions? Okay. All right. So the question we had just before, there are many variations on this trotter step, and this is also an area of active research. The idea is, you know, as we had these questions on this side, is like, you want to choose the best path between your initial state and your final state. Can you like optimize that in some way that you know what circuit to execute? And the answer is yes. I'm just going to talk about two very different methods that are kind of on the other side of the spectrum. There's a method called Q-drift, where you can choose the terms in your trotterization randomly with certain probabilities that are based on the strength of the interactions. So you kind of get the most important things there with higher probability, but you're randomizing it over a lot of things. And by randomizing over the non-commutation of these terms, you actually get less error. So in some sense, the randomization is actually a very good thing. And people do this with a lot of problems these days. And this is only a few years old. This is very active area of research, but this is a, you know, kind of a well-known randomization, trotter randomization technique. There's another one I like because it's not random, but it's a certain way of ordering the Pauli terms of your Hamiltonian in such a way that the circuit that you will synthesize from that will be very amenable to optimization. And this is from some colleagues at IBM, and Gyushu is a professor at Penn now. So you can get these like gate cancellations. You can get terms that will cancel between adjacent terms if you order things in the right way and you think about laying out the problem from the start. That's why when you think about mapping these problems, you kind of always have to like look a little bit of ahead, because maybe you can gain some advantage in your synthesis step because you're free to change the order of the terms of the Hamiltonian for your trotterization. So this is one of my favorite examples from that. So random is also good. Knowing what you're doing when you lay it out is also good. There's and there's a whole slew of things between these two. I just wanted to pick up these two. And I got a question in the back. The idea is kind of like you have a Hilbert space you want to get from initial state to a final state. If you randomize and just select the important terms, you can kind of average over all these things. When you calculate the result you always get out is classical. You can always average over it, and you can always do a lot of tricks. In fact, that's used for error mitigation a lot too. And in some way, if you average over the errors, you get closer to the right answer. That's hand-wavy experimentalist answer. Okay. Cool. Okay, so now we're going to finally move this to a quantum computer. Okay, so when you synthesize these circuits, you're going to break these down into, well, this can be any arbitrary number of weight terms, but we'll start with two. So I write my Hamiltonian terms, and I get something that's like a ZZ interaction, and the strength of it is given by theta, so it's a rotation angle, but that could be corresponding to time, for example. If I just want to implement that on a quantum computer, all I need is a C naught, a Z rotation on one of those qubits by amount theta, and another C naught. That gives you a ZZ interaction. That is like the most digital kind of quantum circuit you can think of. I'm not exploiting any interaction of the physical system. I am just laying out a circuit. From these ZZ type interactions, we can build anything else we want. And so, for example, I can take like X and Y gates, which are just going to be, you know, throwing Hadamards on either side of those Z's, or square root of X's and X daggers on either side of those. And I can say create an XY interaction just by adding single qubit terms. So like in the Hilbert space sense, these are locally equivalent rotations. So you can translate one into the other with single qubits. And then you can build an arbitrary number of them from this kind of ZZZZ picture. So for any qubit you don't have an identity on, you just put a Z, put a C naught on either side, and you have this kind of structure. And you can, I mean, this isn't the only one that would do it. You could have slight variations of this, but basically that's the idea. And basically, because we have limited connectivity, you usually just want to put the C naughts next to each other. So you go from a Hamiltonian to a Pauli Hamiltonian to breaking it up in some trotterization type method to building the circuits of the terms out of things that look like this. And now you have a quantum circuit. So at least we're there after an hour. Any questions on that? So that, yes.
How do you figure out the order of the CNOT? Like I can make any of this stuff. Other
All right, the question is, how do you figure out the order of the C naughts? In these kind of things, you have the freedom. So that's one of the reasons why like the lexicographic ordering is very good. If you have the freedom to choose these, then you can synthesize things that are more optimizable, I would say. And one of my optimization examples exactly shows you that freedom and how you can mess it up. So I hope that will answer it in a moment. Okay, maybe I'll just go through these relatively quickly because you guys probably know quantum phase estimation. Quantum phase estimation, of course, is the oldest algorithm for doing universal quantum simulation. And we have a circuit that looks like this. And we're preparing a state that looks like a bunch of zeros and ones on a register of n qubits and a simulation register given by the state psi naught, which we prepared. By doing these controlled polys here, we can construct this state where we're just acting the powers of the unitaries on the one state of those terms. And because of phase kickback, which ends up being e to the 2 pi I times the, I want to say the bitwise importance of those phi terms. And because of phase kickback, we actually turn it into the sum of e to the 2 pi I times j over all those phases, and those j's are given by the those are basically the bit string, sorry, the number bit strings of all the possible states, and we can quantum Fourier transform that so that when in the measurement basis we get the phase which is in a binary representation. I'm just going to breeze through that, but that's the basic problem. The things to think about for most of these problems is that a lot of times if you want like eigenstates of these things, or all the times, this wave function needs to have an overlap with the eigenstate of the eigenvalue you want. So you have to start with some state that has some initial overlap, which is one concern here. But other than that, that's not much of a concern because no one's going to execute this on any kind of near-term hardware other than the most like small cases. So what I really like to move on is to more closer to what people think about these days, such as the Hadamard test, which is kind of a variation of this, but a little bit more amenable to hardware, where we start with a single ancilla qubit in the 0+1 state. We prepare our state psi, and then what we're going to do is just a single controlled evolution of that simulation register by e to the minus IHT, whatever we got out from our circuits and stuff like that. We put a control on that, we evolve it, and then we measure the x and y bases of that ancilla. And by measuring those kinds of things, we can write the poly x and y in the Dirac notation here, and we can calculate these expectation values. And we find when we do that, we get the real and imaginary parts of that expectation value. And so in some sense, your result of this is you're actually paying for this in the sense that you need to run this for many, many, many times, and you will get some sort of evolution in time of these systems. And from that evolution, you can take a Fourier transform and you can get the eigenvalues or the correlator or the structure factor that you want to get. So the thing is you have to run a lot more experiments in order to get a time function. But this is typically common in quantum simulation. You're going to look for some sort of oscillation. You're going to do it as a function of time because the quantum Fourier transform is too expensive to run on near-term hardware. So you sacrifice the inability to have that for the ability to just do a lot of experiments and then do the Fourier transform yourself, basically. Yeah. Okay, so the question about VQE is how does Qiskit calculate VQE? No, I'll come to that example in a second. Yeah. So what the observable is here. So these are kind of called indirect observables because the one thing you're doing is you're preserving your simulation register. These things are not being measured here. You're only measuring this ancilla qubit. So you still have available the quantum state at the end. it is preserved, whereas in what more called direct measurements, you're destroying the quantum system when you measure it. So I'll show that in a second. So there's a variation of kind of the Hadamard test to calculate correlation functions. We start with the same kind of thing, but we do our controls on the observables instead. So I have two observables like O of A, it goes on to the 1 qubit. Then I do time evolved, which is uncontrolled. And then I do a zero controlled observable of B. So that goes on the 0 state. And then similarly, I can measure the X and Y of these things. And if I calculate all those things, I could find that at the end of the day, I get the real and imaginary part of these correlators. So that kind of just shows how these circuits, theoretically work to produce the observables that I want to do. And then there's the easiest version of this, which is just I time evolve, and I measure in the Pauli basis that I want. And so for VQE and for a lot of what we want to do today, this is the easiest thing to do. Instead of having a controlled evolution of something where we have we're going to look at the phase of an ancilla qubit, that's very hard because those decohere. It's much easier to measure directly measure the observable that you want to on these qubits. You're destroying it, but it's easy to do a lot of experiments, so you can just do that. And it's harder to extract the information out of the ancilla qubit. So and it also opens you up to the possibility of a lot of error mitigation techniques my colleague Vivek will tell you about. So there's reasons we like this, and we kind of try to move towards these kinds of things. And of course, you get the observable out there, which you can think about in the Schrödinger or Heisenberg picture. Should be easy to see from there. So we're going to talk about optimization, and I'm getting a little low on time, but this part is shorter. Yes.
So, does there some problem, or do there some problem exist that I need to maintain the input without destroying it into like measuring it?
All right. The question is if I want to preserve the input and measure without destroying it. Yeah, there's lots of reasons you'd want to do that.
Not the ancilla, but can there be some problems that I have to use this kind of technique instead of just measuring?
Right. I mean, you could think about this technique as so in order to preserve the state, you could think about using this as a state preparation technique, for example. This doesn't have to be the evolution part of the algorithm. It can be the state preparation, and then you want to use that state for something else. Other algorithms, such as linear combination of unitaries, well, that's more of like there's a little bit of feedback between these states and stuff, and I'm going to touch on it a little bit. But yeah, there's lots of applications why you would want to essentially prepare a state and then do something with it. So evolving it is one way, projective measurements is another way. Yeah, I'm sure I could think of something that you would want to do with that. Okay. All right, so let's talk about optimizing. So I'm a hardware guy, so I can answer all your hardware questions at some point. But what we're going to do basically is we're going to take these circuits that we built to do quantum simulation, and we're going to move them to a quantum computer via something called a transpiler. A transpiler is a thing that takes a quantum circuit to another quantum circuit, but that second quantum circuit is one that actually runs on hardware, meaning it consists of like single and 2 qubit gates. It's been scheduled in time. It has a limited set of instructions, for example. And I'm going to tell you kind of like a note on errors. So something I wanted to, kind of highlight the way you kind of approach these problems, especially on near-term devices, is different than you will approach things in the future. And this is going to be an evolution during your careers while you're, quantum researchers and such. You will see this change. And I just wanted to share my perspective with you. So on current devices, I think this is true for IBM hardware, but it's probably true for all or almost all the quantum hardware out there, is the entangling gates have the highest error. So for example, if you look at our backends, we have an error on the order of 10 to the minus 3 for our C0 or our controlled phase gates on IBM devices. We're moving from controlled not to controlled phase. So the error is going down. It's about 10 to the minus 3, but that's the kind of the largest source of error. The measurements error is a little bit higher, but you can always average over that. So that's not a concern. Well, that's a concern for quantum error correction. When you're executing these algorithms, I think about this as being the worst thing. Your single qubit gates have an error about 10 to the minus 4, so about an order of magnitude lower. So you just kind of forget about them. I mean, if you're really trying to squeeze performance out, you know, I would be concerned about them, but normally you would focus on the larger source of error, which is the entangling gate. The interesting thing is the Z rotations are free. We actually track the phase in software, and Z rotations are equivalent to a frame change of the phase of the system. So we actually just monitor that, and it's a 0 time duration gate. It happens in software. It has 100% fidelity. That is a trick we learned a few years ago, and we implement all our gates this way. So Z rotations are free. Entangling gates are expensive. In the future, when we have fault-tolerant quantum computers, the non-Clifford gates are the most difficult. So the problem there becomes you can error protect a limited gate sets that you can implement on your quantum computer, but that set does not include everything you can do. So in particular, people talk about T-gates, which are Z rotations of pi/4. Those must be distilled, and it takes a great vast, that takes a large amount of resources, and it's something I don't completely understand. But I can point you to the right papers if you want to think about it. So these kind of non-Clifford operations are very difficult, but your fault-tolerant operations, such as your C-naughts, you will exponentially suppress the error of them, but you will still have a logical error rate. And this is one thing I always want to point out. Even in fault tolerance, you have a logical error rate. It's just much, much lower. So when you talk about you know, certain depths of code, such as what John was talking about yesterday, you get in the range of like 10 to the minus 8 to 10 to the minus 12, but that's still limiting for some algorithms. You will still have to think about the logical error rate when you do this. And we're going to evolve from this case where we have, you know, basically entangling gates are hard and Z gates are easy, to the opposite situation where entangling gates are easy or error protected to the tune of 10 to the minus 10 or so, and Z gates are really hard and take a lot of resources. So, you know, something to think about in the back of your mind is that the paradigm is going to shift a lot in the way you optimize for these things, depending on where your major sources of error are. So my major source of error is entanglement, so I'm going to try and do as little bit as possible. Okay, so one thing you can do, and this is just like to highlight a couple sources, I can share more, but I don't want to go into great detail, is basically there are schemes for removing the ancilla qubits and do these direct measurements that you would do like for VQE as noted. But they typically require a lot of tricks and could be dependent on exactly what you want to measure. But one thing, some of them I want to highlight are shadow spectroscopy, where you can use shadow tomography, not show tomography, to filter the results to calculate the differences between the square of the density matrices in different ways. I gave you the references, but I don't want to go into these. We can do other things. One of the ones we like to do is we can, if we have certain properties of the Hamiltonian, such as the square is equal to the identity, we can project into the eigenbases of those Hamiltonians. So we can take something that looks like this Hadamard test circuit, and we can remove the ancilla and project and turn it into projection measurements where we can either post-select or we can like dynamically figure out whether the state is in a plus or minus 1 eigenstate of these M or this M operator, and then take the difference and get the result that we want while getting rid of the ancilla. And then that gives you the real part, and then if you shift it by pi/4, you can get the imaginary part and do the same thing. You can do other tricks such as complex time evolution. So this is a trick where you do our normal real-time evolution, which is e to the minus IHT. You can do imaginary time evolution, which gives you the e to the minus HT, which is not unitary, but there are ways you can approximate it. And if you can combine these two ways, you can use some complex analysis tricks to get a more correct answer. And you can see that these are all like very recent techniques. This is a very rich part of the active research into this area. Another thing we can do is we can be more efficient about, we have some sort of observables that I represent by these polystrings. What we can do is, or how we actually implement this on hardware, is we do a basis rotation at the end. These don't have to be polystrings, but I'm just using it as an example. We'll do a basis rotation and then measure in the Z basis because that's the one the hardware gives us. So you can think about, well, if I have like 3 poly terms and that's my measurement I want to do, I've got 64 terms. It's 3 to the 4 terms. 4 to the 3 terms. Yeah. And you can see them right there. But what I can do is I can actually do these measurements, and then I can extract commuting observables from the same measurements. So with just 17 sets, I can measure all 64 polys, for example. so we have, building software and tools that allow you to do these kinds of things that I'm going to show you in just a moment. And, as a hardware guy, I think about like how you build the devices, which probably I can talk to you during the break or after the sessions today. But each one of these transmons that we build, it has a certain frequency, it has certain decoherence properties, it has certain measurements fidelities that how do you get the state out of the qubit. It has higher order levels that are usually a bad thing because we can leak to them, and that's outside the computational subspace, which is not good, but they can also be used for fun things. And then we have the interaction rates, which dictate how fast we can do. So we have certain, on our current hardware, we have fixed frequency and tunable frequency couplings. They implement two different kinds of gates, but those couplings will essentially dictate how fast can I start entangling these things together. And you want to make it fast because you're always decohering during that time. But you don't want to make it too fast because usually things will leak to the higher order levels of the transmon. If you make it too fast, things get a little crazy because you'll have a higher order or Fourier components that can excite you to different transitions. And then you have what you want to do. So a lot of what I do with my life is trying to figure out, I have this device, I want to do this algorithm, how do I actually feasibly do this? And that's kind of what optimization is. And I'm just going to talk about a little bit because Vivek's going to cover some of this, but basically I think about where the errors in quantum computing come from. First, you want to be smart about which qubits you use. There's a lot of ways to break down your circuit into ways that you can map onto a limited connectivity subset. And there's actually algorithms that will help you do that. I'm going to talk about that. There's other things we can do, which we call error suppression, which Vivek will cover, where you can use physics to reduce errors. We can try and understand the noise of the system and to mitigate it. But I'm just going to talk about the basic error rates in this talk. And then we have error mitigation, which Vivek will also talk about, where basically we're going to run the same circuit in different ways and analyze it. So in some way, I think about transpilation takes these circuits to a smarter circuit, a better one that will run on given hardware, less C naughts, basically, less time. And then there's error mitigation, where if you run the circuit in different ways by transpiling it differently, then you can affect the effect of noise. And if you have a model of the noise, then you can kind of either invert that noise, or you can try and take that noise in the limit where its scale is 0. And that's basically what error mitigation is. So I'm just going to talk about routing. So the worst thing you can have in quantum circuits is a swap, because those consist of 3 C naughts. So even on the best hardware, or at least the one I was using, the minimum gate error is 0.3% per C naught or per entangling gate, which means each swap has an error of 1%. So you can think about how all these things add up, and you ask, like, how deep is the circuit that you can do? So we have a new metric called error per layer gate fidelity, which is probably the best answer for that. But one way I would also just multiply all the infidelities, or multiply the fidelities of all your circuits, and then you can kind of get an idea. So, you can 200 C naughts should be doable, and that rate's always extending. But the first thing is get rid of as many C naughts as possible. So we have a stochastic, so mapping these circuits to a lattice is actually an NP-hard problem, but we have stochastic algorithms that are really fast, and they're written in Rust now, so they're heavily parallelizable. But one thing that was mentioned that I wanted to highlight is when you as a quantum researcher want to put a quantum circuit down, and you have limited nearest neighbor connectivity, you have a choice to create a 5 qubit GHZ state. You can do it like this, where you have C naughts coming all from qubit 0, or you have this kind of ladder structure where they're between each other. And that is something that basically those are different graph structures, and none of these algorithms that work on graphs are going to save you from this initial choice. It does not know what quantum circuit you're trying to do, that you're trying to create a 5 qubit GHZ state. It just knows the connectivity of these graphs. So at the outset, you have to be smart enough to give the optimizer something that it can work with. So if I take that bad example and I try to I just draw it and create a quantum circuit, I can, easily see that even the best transpiler level that I have in Qiskit, I'm going to get a swap, because basically the most connectivity any qubit has is 3 other qubits. So there's always going to be a 4th that's left alone, and I need to swap the information between. The other one is you can pick the best qubits that you have. So this is the Sherbrooke device I was using, and we have the error map of that, which we can analyze all the error properties using another algorithm called VF2. It's also another stochastic algorithm, and it can score the layouts and pick the best circuit that you have. And it gives me these layouts of these are the qubits that I want to use for this GHZ state, 33, 38, 39, 40, 41 with its infidelity score of 0.11. So I'll compare that with 1.0 and an average. The average error would be 0.4 if I just looked at all of them. And then some of them actually have bad connections given by the white. So here the T2 is given by the depth of color of the qubits, and the 2-qubit error is the depth of color of the connectors. Okay, so I'm running a little late. So how do we want to do this? Because I haven't gotten to the tutorial yet, but Vivek and I were going to combine that anyway. So we could probably just combine them at the end of next. Okay, yeah, let's just do that so that maybe I can have time for a few more questions. So if there's anything I want you to take away from this, is that there are paths to exploring quantum simulation on near-term hardware, which is exciting because we can't just kind of like, sit around waiting for, the best fault-tolerant systems to come out. We need to do something in the meantime. Then I want to plug a little bit of Qiskit. Qiskit 1.0 is out. A stable version was released just a few months ago. I highly recommend you create a new environment and install it there. Don't just forget about any other version that you had before. There are guides to upgrading these systems. We also have the Qiskit runtime primitives, which actually do the execution. These have also been updated to a V2, which we'll show in the notebook. And then we've improved the documentation, so there's a lot richer and more informed, I know because I wrote a lot of it, about how these things work, so that you can read them on the IBM website. And I hope, feel free to give us feedback and let us know. And also we're talking about scaling, or Vivek is specifically talking about scaling systems up to very, very large systems. And that's something we're very interested in helping people out with. And, this talk is supposed to be kind of a preliminary thought on like how you would do that. But we have a lot of other techniques we're thinking about, educating and enabling people to use the systems as best you can. So there's my email address if you like it. And you can take a picture of it while maybe I have a question or two before Vivian kicks me out. Yeah. Yes.
Great talk, by the way. Fantastic.
Thank you very much.
Can you please share the slides?
I'm sorry. I usually we're not allowed to share the slides, but this will be on YouTube, so you just watch it again.
Okay.
I can show the references.
Okay. Yeah.
Which is where I took the slides from anyway. Yes.
Some pictures for my-
That's fine. Well, we can the YouTube on this. You can do whatever you want. I just can't show the slides. No problem. Yes.
So the way I understand it right now is that we're just taking a Hamiltonian and we're mapping it into a set of two states.
Yeah, so like your mapping is to a poly basis, and then that poly basis has limited connectivity and it has Trotter error. And
we have all these different types of. Is it possible for us to start saying things about like, the general process of mapping any Hamiltonian to some set of end-state systems?
Okay, so the question is about mapping a general Hamiltonian to a set of end-state systems, not without fault tolerance. So we're in this kind of area where everything is a bit more bespoke, and you really have to think about, kind of what you're doing. And that's why there's so many, so much research in the area, because people are figuring out the best cases in certain ways. And I would say a lot of what we do when we figure out these best cases is sometimes we do get a good idea and then we can like encode that in software. So like this error mitigation stuff, for example, it's not quantum simulation, but it's things we can encode in software and make things better generally from the learning we have.
So I guess I think not necessarily say like if I have a Hamiltonian, I can that there is a process that exists that maps to some set of state, and she gets like
Oh yeah, just take the easiest one. That'll map, yeah, but it won't work well, but it'll map. Yeah.
Is there any research going on in machine learning for the transpilation?
Absolutely. I'm glad you asked. Sorry, maybe I don't know if you saw it on the slide, but we do have a custom AI transpiler pass that IBM wrote. I think just released it. You should be able to just find it on with a web search, or I can show you later. AI transpiler, I think will get you there. Quantum maybe. So the question is about AI for transpiling. People are using AI for everything. People are using AI to find the Hamiltonians, to simulate things, to probably find the right order of terms. Like anything you are thinking about today, people are thinking about AI, applying AI to it.
I've got 2 questions over here, and then let's take what's left of our break after that. So.
Yes.
You know, like time issue or no errors. Like, is that really true in the physical system?
Okay. So the question is about feed forward and about the delays and any errors introduced. So that's a great question. So we actually do have feed forward capabilities in our system. We call it dynamic circuits. And the idea is that you can do a measurement of a qubit or some set of qubits, and then you can act on, you can branch off the result of that measurement. So you can do kind of like an if-then type statement. And then in that sense, you know, theoretically, you see, you can just do feed forward, but actually, when you do these problems, you're going to have, a bunch of problems adding up. Basically, you have the length of the measurement, which means all the qubits aren't being measured or idle; they're decohering. So you want to do some error suppression probably while you do that. You have the measurement error. Our measurement error rate's like 1%-ish. So, but you have that. You have some latency in the classical control hardware. You have, kind of these feedback times and latencies that you will have to consider when you're doing it.
Standby, submitting to your circuits to do that.
Oh, the question is, do you have a classical computer on standby? Yeah. Right. So the question is like, where is the classical computer? The classical computer is the one that is generating all these microwave pulses that are going into the system and affecting things and then processing the results. So the classical computers are always there in the background, especially to this feed forward, because that is a very tight, like low latency. It needs to be time-wise deterministic, so it's usually programmed in FPGAs instead of CPUs. There's a lot of considerations that go into that, and that's a very, kind of difficult thing. But in the greater sense, all these gates, all these circuits I'm showing you are going to be represented by delays and microwave pulses and phase shifts and measurements. And those are things that are coming from a waveform generator, basically. And then last question.
You are like talking about Q-Skill project. Is there any way that as a designer of algorithm that we can automate data clear and automate add some like new idea is like some always affecting like popular life?
Yeah, so the question is about developing algorithms and adding to the Qiskit community, and that's a great question, and that's actually something that I also work on. We have something called the Qiskit ecosystem, which is a website. I think it's on the IBM Quantum. On top of Qiskit. And we, of course, welcome people building on top of Qiskit. This is something that makes me very happy. I work with a few of these repositories myself with external people. And one of the other things I would like to kind of highlight here is there is a newer way to interface your repositories that you might have with Qiskit. They're called plugins that are used in the transpiler. So plugin is like the software term, but it basically tells the Qiskit transpiler to use, say, your repository to do a certain task. So for example, I'm working with like Lex Kemper at NC State on this. He has some Cartan decompositions of unitaries that I think is cool, and he put it on GitHub. And I'm like, hey, let's make your GitHub repository consumable by Qiskit. So we're doing that. It's actually just a few lines of code, but you kind of have to explore and figure out how to work on it. So his students are doing that right now. So thank you so much. Thank you for all your questions. I'll be around. Let's just take a break because that was a lot.
Slightly short. Yeah. All right, folks, we'll take about a 10-minute break and then proceed. So